actually do much more complicated. One of the challenges with this approach is that multi-source applications are very computationally intensive. So here I have some examples. You can see here the Sentinel-2 data. So this is spectral data. This is data such as that which is doing your eyes, for example. It's not very easy to see, but there's a line going up and down here. We can actually create a much nicer curve of NDVI with that line. And you can see here, for example, this is over time, and this is the NDVI. You can see that you have one growing season here, and then it drops, and then you have another increase in NDVI there. That might be a growing season, or that might be just crop cover, for example. Here we have a signal Sentinel-1. This is a radar satellite. And you can see here the signal is very, very noisy, but actually we can extract a very clear line from here. So if we think of the ultimate application for this data as crop type maps, so this is Ukraine. This is all of the crops that are grown in Ukraine for a specific year, and this is done at the pixel level. That's our end goal, and the sensors that we have available to us are the Sentinel-1 and Sentinel-2. So the first thing we would have to do is actually pre-process this data, create curves that are more correct, that are more depicting of what's happening on the ground. We have to calibrate the data, and then we have to combine it with other data such as meteorological data, also a digital elevation model. Then, because we can't put all of this data into a model, it's way too much data, and it's not necessarily important for the model to know every single day which NDVI there was. Because it's not important for the model to know that, we actually have to summarize these features. So what we do, for example, is we take the 90th percentile, we take maybe the 10th percentile, 50th percentile, standard deviations, mean, median, mode, all of these descriptive statistics of every satellite layer. We combine that with training data. So training data which says, in this location this year we had maize growing. In this location this year we had sunflowers growing. In this, that will take all of this data as input. You can see that we co-register and create this EO features. We can train this model, and we can apply it to a larger area, and then the end result is this crop type mapping. Ukraine is not a small country, so doing this process over a large scale, the training of a model, but especially the extraction of all of this satellite data on a pixel scale, is an incredibly computationally intensive process. So this is done at a 10-meter resolution here. We have also done this at a world scale. So not just Ukraine, but everywhere in the world at a 10-meter scale, which means that every pixel is just 10 meters. You can imagine the size and the amount of data that is required to process this. We cannot gaming laptop. You will not be able to process this. So that begs the question, how do we do it actually? How do we process these vast amounts of data? We cannot do it on a desktop. However, what we can do is an approach process. We have, for example, you can see it here in green. This is a satellite image of a location, I don't really know where. But you can see that the whole tile is here in green. What we do is we send this tile and the processing instructions to our central node here. And the central node will then break up this tile into smaller subtiles. So you see these blue squares. So it's much smaller pieces of the final tile that it will then send to processing nodes. And these are pretty much smaller computers. that will then perform the actual processing. They will send the results back to the central node. The central node will stitch everything together, and it'll give you a result back. That way, you're not relying on one computer to do all the processing. You're distributing the processing between many smaller computers. So this is really the foundations of the ideas behind cloud computing, is that once you cannot process things on your desktop or in an easy to access way, you have to use more distributed methods. So this is something called parallel processing as well. And so it relies on this setup, which is also called high performance clustering or high performance computing clusters, HPC. The challenge with these, it's not going to be that easy just yet. The challenge with these HPCs is that they are incredibly expensive. They are very difficult to maintain. We have a server room with one of these HPCs in our office, and it's a massive room, maybe twice the size of this one, with incredibly energy-intensive air conditioning, water cooling. You need experts, you need many, many experts to be able to run this. In case anything breaks, you need people that really are experts to know how to fix it. You need very regular maintenance, and you also over the internet to be able to get the data. Because at the end of the day, you're still downloading and uploading data, so you're constantly going back and forth over the internet. Because, for example, if we have this cluster in our office, maybe we don't have access to this Sentinel file. We don't have it saved in this cluster. So we have to still reach out to the internet, get the Sentinel tile from the internet, bring it into our central node, and then distribute the processing. When you talk about something on a large scale, such as in the entire world, for example, or even something like Nigeria or Ukraine or Belgium, it's still a lot of traffic going back and forth over the internet. And also, one thing to mention is that these systems, because they're localized, they're sensitive to two things which are relevant here, and that is power cuts and issues with connectivity, obviously. Unfortunately, these are realities, so if you have power cuts on an incredibly power-intensive and power-hungry system, that makes your life a little more difficult, because obviously if you're starting to process something and the power cut happens, you have to start from zero again. So the solution to this problem, which is that we can't use our desktops, they're not powerful enough. We can't really use HPCs anymore because it's too much data, it's too localized, and it's too much traffic over the internet. The solution is actually cloud computing. And this is the main focus also of our talk today. And what is cloud computing? So it's actually the on-demand availability of computer system resources, especially the data storage and computing power, without the management by the user. What does this mean? This means that you, as the user, can access data that's located on the internet. So Sentinel data, satellite data, doesn't matter. You can access it, you can conduct processing operations, you can extract information, you can train models, you can apply models, you can download the results, and you don't need the IT expertise to be able to run these HPCs or to be able to do all of the pre-processing steps yourself. This means that it's much more accessible, much more open, and pretty much anyone that knows a little bit of coding or that is interested in learning a little bit of coding, a little bit of programming, can actually access this data. If you take a training course online, within 5 minutes you can probably start to access and play with this data. It's very, very accessible. How can you access this cloud computing software? There is a huge variety of providers. We will talk specifically, Kun and I will talk about two of them, and this is the Google Earth Engine. This is probably the most accessible cloud computing option. This one, you just need an account on Google. You can go onto Google Earth Engine, and you can actually start immediately. As long as you have an internet connection, you can access satellite data, you can download it, you can process it. It takes a few minutes to extract a certain area and already have that satellite imagery. And the second thing that we'll talk about is the OpenEO platform, and this is a part of the Copernicus system. I'll describe it in a second, but what it is it's the European Union's answer to Google Attention. The challenge with Google Attention is that it's a product of Google. Google is notoriously unreliable in terms of keeping up their programs, keeping up source of their programs, and it's a private company at the end of the day, so yeah, we never know really what it will lead. OpenEO and the CBSC, it's a publicly funded alternative. It's also free to access. You get some credits to process data directly. So there's many other services that you can also use. I won't really go into detail about those. Talking about the Copernicus data space ecosystem, this is an ecosystem that's built on the idea of cloud computing. And it has a lot of different nodes, a lot of different options, a lot of different parts to it. Some of these, for example, is, as I mentioned, the Sentinel data. This is the flagship satellite constellation of the European Union. So all of this data is stored within the ecosystem. The Copernicus browser, which I'll show in a minute, it's a website where you can actually access this data and you can visualize it, you can look at it, you can access the entire catalog all over the world, and you can already do some basic analysis steps without knowing how to code, which is, I think, really important. It also includes additional EO data from other satellites, from American satellites, but also from different stages, different missions of satellites. What I think is also really important, and something that we work in a lot, is that there is online code labs and interfaces as well as training programs. All of this information is incredibly accessible. All you need is an internet connection. That's really it. Even with, one of the benefits is that even if your laptop is not very powerful, as long as you have an internet connection and you process web pages, that's it. That's all you need. All of the processing power is happening in the cloud. That's the biggest benefit of this cloud computing, is that you don't need to worry about your own computer. All of the processing power, all of the resources are happening in the cloud. You just access those resources. That's the really big benefit. And so this onboard code repositories and code labs and